Welcome everybody to this Europractice webinar. My name is Maria Martinez Balado. I'm a program manager at IMEC and Europractice, and I will be your host today. Today, we have a new episode of the Compound Semiconductor webinar series of Europractice. This series started last year, already in November, first with an introduction to compound semiconductor materials, applications, and a market overview. And then in December, we had a second episode dedicated to 4H silicon carbide CMOS technology for harsh environments, with a special focus on the technology developed by Fraunhofer IISB, which is offered via Europractice. These two webinars and all the others that we have done in the past are already uploaded in the Europractice YouTube channel, so I invite you that after the session of today, you go there and check your favorite episodes. And by the way, the episode that we are going to see today will be also in YouTube by the end of the week. So speaking about this, today we have another special episode because it is dedicated to a specific technology. This time we will take a deep dive into gallium arsenide technologies for power and low noise RF amplification, putting a special highlight on the technology offered by United Monolithic Semiconductors Foundry, also known as UMS, which is the affiliation of our speaker, Dr. Leclerc. Speaking about him, it is my pleasure to introduce all of you to Dr. Eric Leclerc. He was born in France and he's a physicist by training. He obtained a research degree in physics in 1984 and a diploma in solid-state physics in 1985 from Paris-Sud University in Orsay. After that, Dr. Leclerc pursued a PhD and he did research within Thales, where he was working on gallium arsenide LEC monocrystal growth and defects influence on transistors. Once he finished, he joined UMS at its very creation in 1996 to work on new 3.5 power device development, characterization, and nonlinear modeling. Nowadays, Dr. Leclerc is the field marketing manager within the UMS organization, mainly for defense, space, medical applications, and Foundry. And prior to this role, he also was working several years in UMS Foundry service as the manager for quite some time. So with that, I have concluded my part, and it's now time for me to pass the baton to Eric. I wish you all a very nice webinar, and Eric, when you want, the floor is yours.
Thank you a lot, Maria, for this nice introduction. So I'm very pleased to be there today, and I would like, of course, to thank a lot Europractice organization for that nice opportunity to show something I hope will be interesting about transistor optimization for a specific domain, which is RF and millimeter wave. So let's see now the agenda for today. So after introducing UMS, our market, I would like first to remind you what is a transistor. And we will see the ultimate performances expected in the different domain where we use a transistor. These domains are very different, you will see that. And of course, in our RF and millimeter wave domain, which is a bit specific compared to the others, which are, I mentioned, digital and power applications. So I will explain why pHEMT is preferred in regard to the MESFET, and how technologies are optimized for the RF and millimeter wave applications, which are in two directions, low noise and power, RF power. Device modeling also is a challenging mission for our RF and millimeter wave. I will show you a few things about modeling. And finally, I give some examples of the applications we can address with these technologies. So let's start now with a short introduction about UMS. UMS is a joint venture which was created more than 25 years ago. It's created by two big mother companies, which are Thales and Airbus. So UMS is a German Franco company with main offices in Europe. We have sales office in Asia and in the United States. We are leading RF and millimeter wave solution suppliers for our mother companies, of course, for defense and space, but not only, for different applications. We will see that next slide. We have proprietary GaAs and GaN technologies, which are also qualified for space. So they are part of the what we call the EPPL, which is a list of preferred process managed by ESA and other space administration. So manufacturing is fully in Europe, sales office in Europe, in USA, in Singapore, and we have a lot of, I would say, expertise inside UMS. We have expertise here in Villebon in France, but also in Ulm in Germany. We have expertise about modeling, about 3.5 technology processing, I mean GaN and GaAs. We have expertise around the packaging, MMIC design, back-end operation. Back-end means on-wafer test, dicing, picking, inspection, and up to the packaging. And also, because we have our process open in Foundry mode for a long time, a Foundry service fully dedicated to customers. So our market now, I don't want to spend too much time on that, but let's mention that for sure with our mother companies, we are covering defense and space, which is a bit strategic in Europe, but we have also some other applications which are creating volumes like telecommunication, where we are in the backhaul and fixed wireless access. Within the automotive market, where we were leader in the long range and short range 24 and 79 gigs radar before the introduction of the silicon solutions, and some others which are growing slowly but surely. In the industrial domain, we provide level sensors, smart cameras, speed radars. In the medical, which is growing also, some smart pills or sensors for imaging. Test and measurement, for sure, our products are welcome for wideband amplification, for portable equipment. And finally, I mentioned also drones, where we need to identify the position of drones. We need to measure the distance from the ground to the drone and so on. So let's say a few words about the sales. It's about, you can see on the right, about half of the business in UMS is dedicated to defense and space, not only in Europe, also covering the United States and a part in Asia, where the rest is between commercial applications, something close to 10% for the automotive market, 20% for the telecom market, and about a bit more than 22 or 20% for the ISM and other markets. Okay, so let's now describe our offer. We have a team of about 20 RF designers here in Villebon. And these designers can design power amplifiers, very low noise amplifiers, mixed signal functions, and multi-chip modules for our catalog. We have about 250 products in our catalog, but also they can design on demand for specific requests from customers, what we call the ASICs, which are products dedicated to one customer. The designers have the capability to design on our proprietary GaAs and GaN technologies, you can see there, which are open in Foundry, but they can also use time to time some external process like SiGe process, and in addition, they can play with the portfolio of packaging solution. In addition to the product, we have also the Foundry service, which is a way to open our proprietary technologies to customers who have the capability to design their own MMIC. And for that, what is key is to deliver a good PDKs. I mean by PDKs, process design kit, which is a tool, a file, a set of files which includes all the libraries you need to design MMIC, so electrical model for active device, for passive device, and so on. So we organize also time to time Foundry training. We have a multi-project wafers, especially one with Europractice. I will come back in the conclusion. And we offer 3.5 technologies like pHEMT and HBT on GaAs, MESFET also on GaAs, EMT on GaN, And we have also other technologies like a Schottky diode process and a purely passive gas process. We can deliver wafers, we can deliver dies after wafer dicing. We can also deliver packaged devices according to the customer needs. So really a comprehensive support according to the customer need for the foundry service. So this was really a short introduction about UMS. Today the topic is a bit more technical. It's about transistor optimization. So just to remind you what is a transistor, field effect transistor or MESFET, metal semiconductor field effect transistor. So thanks to the properties of the semiconductor, we can modulate the gate through the gate electrode. You can see here the gate electrode, which is modulating the level and the level of carrier in the channel. This gate controls the carrier concentration in the channel, which means we are able to modulate the current flowing between the drain and the source. The charge to be moved below the gate is proportional to the gate length and is assimilated to a capacitor. What is here the capacitor is a CGS plus CGD, which is the total capacitor of the gate. Of course, when we decrease the gate length, the carrier speed, so the electron speed, increase. This is why it's important to reduce as much as possible the gate length in order to activate and to increase the cutoff frequency. In addition, it is obvious that the total current increase when you increase the transistor width, which we call W here. Of course, the current is so proportional to this parameter W. Access regions are parasitic. I mean, access regions are source resistance here, are drain resistance, are gate resistance, associated, of course, with other parasitic elements like the inductance, like capacitance. Why do we use 3,5 components like GaAs, GaN, or indium phosphide? In some companies, they still use indium phosphide. It is because compared to silicon process, 3,5 devices exhibit very high electronic mobility, which leads to very high cutoff frequency. So now, how do the companies use this transistor in the three main domains, three main worlds? I should say worlds, because it's really different. One is about digital, one is about power, and one, which is the topic of today, is about RF and millimeter wave. So digital and power are very, very big mainstream in the, I would say, market for semiconductor. What is digital? It's to switch from 0 to 1 to make computers, to make processors. So what is the need? It's about integration, and integration implies to reduce as much as possible the transistor size. You just need to reduce the current of the device in order to keep the capability to switch from 0 to 1. Another point is that you need also low voltage. Just to manage 0 or 1, and high voltage are not required. This is on one hand. On the other hand, which is power, and power is used for battery charging, for changing from DC to AC. It's a big domain because of battery charging, because of automotive. What do they need? They need very large device to switch and to use a switch mode of transistor to create transformation from AC to DC or to DC to DC. They use generally E mode transistor, so the enhancement mode, which are normally off, and they need very high breakdown voltage. Why? Because it's a switch mode operating mode, which creates very high voltage compared to the supply voltage. And finally, what we are discussing today is about RF and millimeter wave. RF and millimeter wave is a way to use not 0 or 1, but to use analog behavior of the transistor and of the signal. So it requires to amplify the signal, so generally at high frequency. So it requires high cutoff frequency, high Fmax transistor. There is also something important in this world, which is the 50 ohm matching. Somewhere, more or less, the transistor have to be as close as possible to exhibit impedance close to 50 ohm. This is why in this domain we don't use very, very small transistor. And important also to mention, you will see why now, power and low noise are the two main, I would say, trends in this RF and millimeter wave. Low noise, it's how to amplify a signal without adding too much noise, require high transconductance and low access resistance and low parasitic resistance. On the other hand, high RF power generation for RF, I mean, requires high voltage for sure and high current. I will explain that in a few slides. So let's now be more focused on the 3.5 technologies. Why do we use in the 3.5 technologies the pHEMT, which is a pseudomorphic high-electron-mobility transistor, compared to the MESFET, which was, I would say, the initial device created 30 or 40 years ago on our technologies. In a pHEMT, we create through the gap difference between two materials. So, for example, between AL gas and IN gas, due to the gap difference, when you build this epitaxy, then you create a gap, and this in this position, you can create an electron gas, which is that electrons are confined in the lowest energy region of this conduction band. So here you have a cut of the transistor, which is showing the gate of the transistor. Here, I would say the AL gas region where we have donors like silicium, and then here the channel, which is electron gas, two-dimensional electron gas. This case is with homogeneous doping. We have another trick, which is to replace the homogeneous doping by what we call delta doping. You can see here, the doping is planar, so the silicon are deposited on this plan. And this is very interesting because it's a way to separate strongly the carriers here to the donors, to the electron donors here. And through this separation, there is no Coulomb scattering in the structure, which means the electron mobility is no more controlled by the Coulomb scattering, but is controlled by interaction with phonon in the structure. And this gives a very high electron mobility, especially so in the case of delta doping, because here, in the case of homogeneous doping, you may have still a small interaction between the electron gas and the donors. So these devices, compared to MESFET, can provide a very high mobility and so very good performance for going higher and higher in frequencies. The performance of the transistor, I mean the transconductance, the drain current, the threshold voltage, which is called VT, are controlled by the doping of the structure, here or here, and by the distance between the gate to the 2D channel. This is why we can provide very reliable device with these techniques, because the control of the doping and the thickness can be controlled through the epitaxial process. Now, let's say a few words about the parasitics, and especially the gate resistance. The gate resistance, the gate is there, and you can imagine a gate for a digital device. Here you can see digital device, keep in mind, is a very small transistor. So you can calculate the gate resistance, which is proportional to the resistivity of this metal, multiplied by the length, here the W, what we call the W, divided by this area, which is the height of the gate, multiplied by the gate length. So for a digital transistor, no issue. The gate is very small, so the gate resistance, RG, is small. But for a large device, when we need power, when we need RF power, when we need to be close to 50 ohm, we need a large device. We can calculate again this resistance, which creates a high resistance. And this high resistance is really a disaster when you calculate the cutoff frequency and the maximum frequency of the transistor. How can we solve that parasitic gate issue for large device? We use this trick in our RF world, which is a bit simple. On top of the gate, which is, we call that the gate foot, which is controlling the drain current, we had a big head, which is a gate head. And why do we do so? Just to increase this area. And in order to increase this area through this trick, the trick is that the gate resistance is again proportional to the length of the device, but divided by this global surface, which means we can go higher and higher in frequencies. We still have the gate foot, which is very small to control high electron velocity, but we have a gate head, which is big and which reduce significantly the resistance, leading to a very high cutoff frequency. So we can keep high frequency on the device, even a large device, for our applications. So let's see now one example, which is on our low noise processes. Low noise, what we need is high cutoff frequency, high transconductance, and low access resistance. This is an example of in-gas pseudomorphic heterostructure. You can see here the gate foot, the gate head, all is protected with a nitride on top. You can see here something very important in our gas technology. It's a recess. A recess is a chemical etching near the gate in order to control exactly the distance between the gate and the 2D channel. And you remember what I mentioned a few slides before, through this distance, you can control all the critical parameters of the device. So we call that also a T-gate. Why? Because it's like more or less a T. You have just the foot and then on top the horizontal bar of the T. So really this solution is the best fit to millimeter wave application. It's really high reliability. Why? Because it's fully protected and the gate is fully protected, which is really important to keep high reliability. It's high yield from a process point of view. Why? Because again, this 2D channel and the doping is controlled by the epi and the distance is controlled by the recess. And because this recess is really narrow recess, you can see narrow means the recess steps are here very close to the gate foot. We can keep a very low access resistance in the source and in the drain area. So we keep a very high cutoff frequency. And finally, for the application, a very good noise figure. You can see here the evolution of the noise figure, the minimum noise figure of the transistor, which is a bit proportional to the frequency F, CGS, which is the capacitance from gate to source, multiplied by the square root of the RG gate resistance plus RS divided by the transconductance. So I mean, if I can increase the gate, if I can increase the transconductance and decrease the gate resistance and source resistance, then I can keep a noise figure as much as possible close to 1. Of course, definitely when you increase the frequency, of the transistor, you will see the noise figure increasing. This is unfortunately, but that's physics. So this is how we basically improve and we optimize the process for low noise. Let's see now the different case, which is what about power, RF power, I mean. So you know, basically power is the product of current by voltage swing. So on these characteristics, you can say really basically, and it's of course there are some parasitics, but that the maximum power you can extract from an RF point of view is the product of the maximum current multiplied by the maximum voltage divided by 8. So you remember that with a narrow recess, we may have low access resistance. Now with what we call a wide recess, we can increase the breakdown voltage. And in order to get higher voltage, we need to increase the breakdown voltage. So by a combination, it's a bit tricky from an engineering point of view at the front-end level, but through the optimization of a double recess, we can, you can see here the profile of the double recess. So we still have the narrow recess there, and we have another one, which is called the wide recess. We can keep a good, I would say, balance between the source to gate optimization and the transconductance and the breakdown voltage. This is a way we can optimize both the power density and also the linearity, because for these power amplifiers, what is important also is to keep as much as possible a good linearity. So with gas, typically what we can do is to achieve something like 600 milliampere per millimeter at the transistor level, with a typical breakdown voltage higher than 13 volt and a high power density. We say, generally speaking, that PSAT, so saturated power, is close to 1 watt millimeter on gas, where for the GaN technologies, that is another topic, we can reach 5 to 10 watt per millimeter. So what about now? You can see here an example of a transistor. So the gate width, the length here, and the number of gates. These are parameters. And of course, the multiple finger approach is also a way to increase the total periphery of the transistor without increasing the gate resistance, because the gates are in parallel. Transistor parameters, so number of gates and unitary gate width, are parameters, and MMIC designers can play with these parameters in order to match the circuit and to optimize the circuit. So the impedance matching sometimes can be, I would say, managed through the set of parameters you use. So this requires at the design level very accurate electrical model or electrothermal model, which have to take into account these scalability parameters, W and N. These models libraries, which include other elements like passive device, because of course RF and millimeter wave design requires passive elements like inductor, capacitor, resistor, and so on, are all, so all the models are assembled in what we call a PDK, a process design kit. And in the RF and millimeter wave world, our PDK are supporting two tools. One is ADS from Keysight, this one, and one other is Microwave Office from Cadence. How do we model the device? I would say we have three choices, or physical models, fully physical, which are based on physical equations and parameters. That can provide very accurate simulation, but with very long time for simulation. So that's not suitable for MMIC tools. Another choice is to use what we call a black box model. So you just ask for a time domain or frequency measurement on one topology, and you use this topology to design. Unfortunately, this is not compatible with what we call scalability, the possibility to have model with N and W as a parameter. So it's really limited in our RF and millimeter wave domain. So our choice in UMS is to use what we call the empirical or compact model. This is based on equivalent circuit description extracted from S parameter, from current and from pulse current measurement. This provides good accuracy and a more flexibility domain, and they are widely used in the MMIC CAD tools by our designers, but also by our customers. Extraction is not so easy, depending on the technology. It can be complex model, but finally, with this capability to converge easily, to simplify the approach and to integrate the parameters of optimization, W and N, it's a best choice in Foundry applications. Sorry. Let's see now the processes in UMS. Basically, all the processes in UMS are open in Foundry mode. So we have this pHEMT family that I described today. So here you have the low noise family, pH25, pH15, and pH10, respectively 0.25, 0.15, and 0.1 micrometer gate length pHEMT process. This is why you can see the increasing frequency of use. And here we have the two high power pHEMT processes. So today, my talk was more, I would say, turning around these two families of pHEMT processes. In addition, we have also, I can mention, HBT process, which is used for VCO design, very interesting for low noise, low frequency noise. It's very interesting device for low noise. HPO7, which is an old MESFET process. We still have a MESFET process in UMS. We also have a Schottky diode process for MMIC design. So not only with a diode, but also with some matching element. And the last one is a pure passive gas process, ULRC, which is interesting because it's low losses and high dielectric constant. We also have two GaN processes, GH25, quarter micrometer gate length process, and GH15. I will come back on that on the last slide. So pH10, now what are the main performance and application with pH10? pH10 is a low noise gas pHEMT process, 70 micrometer substrate thickness with a high transconductance, high current. Breakdown voltage is higher than 6 volts. So typically we bias transistor at 3 volts. We have two metal interconnect layers, optional resistance, metallic resistance with different values, MIM capacitors and capacitor over vias and things like that. So here it's an example of what we did. It's a UMS product on pH10. It's an E-band LNA. So in E-band, in this frequency band, 71 to 86 gigs, providing 22 dB gain with noise figure below 3.5 dB. Bias that I mentioned, this one is at 3.5. We also deliver this with protection, additional protection. So pH10 is a low noise process. Also, we can deliver, I would say, medium power. This process is qualified for space. Typical lead time for such single recess process is 7 weeks. And again, we have this BCB option when we need packaging in a molded plastic QFN package. Just to be added, in addition, we are now offering on pH10 a new version, which is pH10-20, which includes new features, new high density MIM capacitor, and the possibility to have capacity over vias, which is a way to reduce parasitics. And also we have the option of what we call hot vias. It's a way to use the via hole not for the ground connection, but also for the signal propagation. Now for power, we have the PPH15X. You remember I showed the trick about the two recess optimization. So this is still 70 micrometer gas substrate, providing close to 1 watt per millimeter. Breakdown voltage is higher, 12 volt. So it means we can bias this device at 6 volt. Also, we have two metal interconnect layers with the same metallic resistance. This is another example, 37 to 40 gigs PA with a 31 dB PSAT, 38 dBm OIP3, which is a way to measure the linearity of the transistor, offering 20 dB gain, 6 volt biasing voltage with 0.1 amps current. This product is packaged in a plastic solution. So this process also is space qualified. We launch on this process more than 100 projects over the life of these technologies. The cycle time is a little bit higher because it's a more complex process. You remember the two steps for the recess, and also the BCB option is offered for packaging in plastic solutions. A few other examples. I want now to show you what are the market or product and circuit you can design. On PH10, the domain of applications are definitely high frequencies, so E-band radio, but also automotive W-band radar, imaging sensors, or optical fiber receiver, I mean transimpedance amplifiers, and instrumentation. So you may design LNAs, mixers, drivers. Just an example here given in this slide is something done by the University of Las Palmas. So here is given the link to this publication. It's a 2-volt LNA for K-band applications, providing 1.4 or below noise figure. And here you can see the example of what we call the matching of the elements. So it's really a clear example of kind of RF and millimeter wave design we can perform on such process. Now on the other processes open in Europractice, but you will learn more about the GaN in the next session next week. On GH25, applications are radar, communication, and also for multi-purpose, what we call transistor. So it's not MMICs, we just deliver transistors or power bars. And you can design an MMIC HPA, but also LNAs. It's interesting due to the very high breakdown voltage to design robust LNAs. Mixers, front end. So front end means integration on the same MMIC. You can integrate the RX and the TX path of a signal, so with the LNA and the PA. High power switches also. And this example here is on YouTube. It's a Plextech or PRFI today in UK, which explains step by step how they did the design of this one-stage X-band HPA on GH25. And the last one, finally, is a GH15, so the 0.15 micrometer GaN process is for radar, communication, SATCOM, also instrumentation. You can design also HPA, LNA, mixers, single chip front end, and wideband PA, for example, for instrumentation. And this last example is was published some years ago by MEC in Italy with Ferrara University and Milano University. It's advanced KU band GaN single chip front end, so integrating both LNA and PA for space synthetic aperture radar solutions. And here also I put for you, if you are interested, the link to get the different publication. So now, again, the roadmap. What is interesting on this roadmap is to mention that you will learn more about the GaN process, I would say, in the next webinar. I think, Maria, you will maybe say a few words about this coming Europractice webinar. And I think it's next week or soon. pH10 gas low noise process is also available, you can see here, through the Europractice offer. So today, UMS and Europractice are in a partnership to offer through the Europractice portal the 3 technologies that are here. So it's a good start, I would say, with 2 GaN technology and 1 gas technology, knowing that all UMS technologies are fully open also in Foundry mode, and that for people who are interested to get, even if just they need to, or you need to try simulations, then you can get PDKs from all the UMS processes for the trials you want to manage. So I think this is my last slide. So thank you for your attention, and I think now it should be the time for questions.